All right, welcome everybody and thank you for coming. We are RescueX and we are with the Autonomous Firefighting Robot Challenge. On our team we have Shervin Hagui, Jaron Givianrad, Shervin Nikravesh, Vincent Thomas, Nico Enriquez, and myself, Alex Camp. Now the challenge before us is to put out a flame located on the first floor of the engineering building. And throughout the course we will have decoys placed. Our robot must autonomously travel throughout the course and be able to distinguish the decoy flame from the real flame. Now, the challenge is in two phases. In the first phase, we have 3 runs, and the fastest of the runs will be recorded. In the second phase, we run simultaneously with the other robot teams. The fastest to put out the flame wins. Now, to accomplish this task, we had to overcome many design challenges. Some of the design challenges are flame detection, figuring out how we need to detect the flame. We also had to figure out how to drive straight. Our robot, believe it or not, is not easy to drive straight. You need to use encoder feedback, lots of different engineering techniques in order to get the robot to drive straight. We also need to avoid objects, and once we get to the flame, figure out a way to extinguish it. By far, one of the hardest things to do is to integrate all the components together to make it work as one unit. To show us how we integrate our components, we have our block diagram. Now, the brains of our robot is the PIC microcontroller. We also use a Raspberry Pi and our phototransistors for flame detection. We use IR proximity sensors for object avoidance, and we have motor drivers that power DC brush motors for locomotion. Now to talk about our chassis and our body, we have Shervin.
Thank you, Alex. When we began this project, we wanted to create a framework that was compact and capable of containing all our components. As you can see, we have done just that. We designed our robot to be 250 millimeters in width, 260 millimeters in length, and 110 millimeters in height. Our robot is fairly small, which allowed us to utilize every inch of space within the chassis. We placed the wheels within the framework to ensure that our wheels are protected at all times. Our sensors were utilized around the front of our chassis, allowing us to give us a wider range in navigation and flame detection. We also incorporated a removable top to allow our engineers to easily have access to all the electronics within the chassis. I will now hand it over to Nico to talk to you about our flame detection system.
Thank you, Shervin. For our flame detection system, we designed it using the Raspberry Pi, which runs a computer vision software that we developed to find flame detection. Our computer vision software involves the capturing and processing of infrared light frequencies. As you can see, infrared light frequencies actually reside outside the visible light range of the human eye. Therefore, we had to equip the Raspberry Pi with a specialized camera called the Pi camera, which has specialized sensors in which it can capture infrared light frequencies and send that data to be rendered by the Raspberry Pi's GPU. The core elements of our fire detection system involve the Python language and OpenCV. OpenCV is the computer vision library that we implemented because it allowed us to perform the various video and image processing functions that we needed for flame detection. Of course, flame detection, image processing, video processing is very computationally heavy on the Raspberry Pi's CPU. Therefore, we had to optimize and simplify our data workflow. Here's the brief overview of our flame detection design. It starts with a video feed that we cut down to 30 frames per second to further minimize the latency of our output. We then extract each frame and break it down into its individual color components and pass it on to our HSB comparison algorithm. HSB is a derivative of the RGB color space. However, it's mainly used to define the brightness of the pixel rather than its color pigmentation. It's important for infrared frequencies because infrared actually lacks any type of color, whether it's red, green, or blue. That data is then passed on to our calibration system, which involves the PIC microcontroller to make the appropriate maneuvers in order to get an accurate shot for our extinguishing system. Here's a demonstration of our flame detection system. In the background, this is a video feed that passes its frames to our traversal algorithm, in which the binary data is broken down into strings and the HSB range that we have defined for infrared light. It is used to find the largest pixel cluster, and a successful detection is exemplified by the yellow centroid followed by the red line. The red line actually spits out the coordinates found of the detection, and it's printed by the software. And we established a UART communication channel between the Raspberry Pi and the PIC microcontroller. And this the coordination data gives us the physical flame position to the robot. The biggest challenge in depending on HSB was that other light sources would actually confuse our algorithm, such as the ceiling lights or reflections off tiles. Therefore, we had to implement secondary hardware with this specialized filter. This specialized filter actually allows the integrity of infrared light frequencies to pass through it while still blocking out all ambient light. And with the detection data, we pass it on to the PIC microcontroller, which Vince will talk about.
All right, so as Nico stated, we are using the Raspberry Pi as our main fire detection system. However, there are some certain features that the Raspberry Pi doesn't innately have, such as ADC and the ability to drive our locomotion systems. Henceforth, we used our PIC32 microcontroller. Because we are using two systems, we needed a way to communicate between these systems. And our solution to that is to create a UART communication link. So whenever the Pi has detected a flame source, it will pass a single ASCII character telling the PIC to move in a certain direction. The PIC then translates that data and pivots either left or right, centering in on the flame. One thing that we noticed through our testing was that the Pi would detect the decoy as well as the real flame. So we decided to come up with a two-layer fire detection system utilizing phototransistors. As you can see, the decoy will produce an erratic pattern on the graph shown to your right. Basically, that red line shows the threshold that is deemable to be a fire. Whenever the Pi has told the PIC that we have centered in on the flame, we activate our phototransistors to store that ADC value into an array and then analyze that data and determine if it produces a range that is similar to the decoy. If it is, then we pivot back on course and continue through our course traversal. Otherwise, we would drive towards the flame and then put it out. So all of this fire detection and validation is great, but if there's no way for us to reach our target, then all of this would be for naught. So the scheme we decided to come up with is dead reckoning. Dead reckoning is basically taking our current position relative to the start position. We do this through encoder feedback. Basically, every time the wheel moves, it produces an encoder tick. We then translate the accumulated encoder ticks into total meters traveled, and that gives us our relative position to the start position. Another thing we've noticed is that dead reckoning alone won't let us fully traverse the course. If we ever encounter an object or something, it would ram into the object and then get us off course, thus producing infinite amount of errors. So I'll pass it on to Alex, who will explain how we utilize our IR sensors and create an object avoidance algorithm.
All right, so for object avoidance, we make use of IR sensors. They are infrared sensors that will generate a voltage that varies with distance between an object. We can then encode, set a threshold that when the object reaches a certain distance, our robot will go into our object avoidance algorithm. Our robot then will go around the object and get us back on track with our dead reckoning system, and thus being able to keep searching for the flame. And to discuss how we're going to extinguish the flame once we do reach it, we have Sherman.
So for our fire extinguishing system, we decided to run it at 12 volts and 1.3 amps. And this gave us enough power to extinguish a flame at approximately 175 millimeters away. And to ensure that the flame got extinguished, we added a nozzle at the end of the pump, and that spread the water, giving the robot a better accuracy to extinguish the flame. And now to talk about the printed circuit boards, I'm going to pass it to Jaren.
Everybody. The printed circuit board is used essentially to create a power and data link between electronic devices. This power and data link acts as sort of the intermediary between the devices, allowing us to fulfill a given function. in our case, to autonomously search a course and to extinguish a flame. We have 2 circuit boards and 2 PCBs rather in total. Our first one is a locomotion board. Our locomotion board runs our DC to DC converters, which will step down the voltage to acceptable levels. And the second thing that runs is our motor drivers, which are then connected to our electric motors. These electric motors are, their speed and direction is varied with PWM. This gives us the ability to traverse the course in the most efficient way possible. Our power source is a 22.2 volt lithium polymer power cell. This power cell creates a very, very high current. So those DC to DC converters are very, very crucial to our design because they create 2 supplies, a 3.3 and a 5 volt supply. The 3.3 supply feeds all those red lines to the Raspberry Pi flame detection camera, to the phototransistors, to the IR sensors, and eventually to our microcontroller. And here to talk about the milestones is Shervin.
Throughout the semester, we set ourselves a series of goals to keep us on track. As of today, we have assembled our chassis and all our components. We have established UART communication with the Raspberry Pi and the PIC microcontroller. We are able to detect a flame and distinguish the flame from the decoy, and we are capable of traversing the first floor of our engineering building while avoiding any obstacles. I will pass it on to Shervin to talk to you about the budget.
So we were given an $800 budget by San Diego State University. We spent the majority of it on the locomotion. We spent approximately 24% of our budget on the sensors, 20% on the software development, which is like the microcontrollers and the Raspberry Pi, and we spent $96 of our budget on the fire extinguishing system, and now we have approximately $32 remaining. So in conclusion, the main goal of our main objective was to maneuver through a course, find a flame, and extinguish the flame. We gave you an overview of how our robot traverses through the course. We gave you an overview of the components in our robot, and we told you guys how we're going to find the flame and how we're going to extinguish the flame. So I hope you guys enjoyed our robot. Thank you for listening.